coincides with the curve. And that's kind of weird that that works that way. All right, so what we're going to do is we're going to turn a line integral into a surface integral. But just like we had this theorem went from this down to like these partials, we have to account for that also. It's really kind of an amazing theorem. Now there are lots of conditions that we have for Stokes' theorem to work. But in the world that we deal with most of our applications in physics and engineering, these conditions are met. So we don't have to be too concerned about it. This is me reminding you of something, don't worry about that. And then here it is. So I'll make this a little bigger. All right, let S be an oriented piecewise smooth surface that is bounded by a simple closed piecewise smooth boundary curve C. Okay, so our surface, we have to start off with a surface, and that surface has to be oriented. So we need to be able to talk about normal vectors to this surface. Piecewise smooth, meaning that it doesn't have any crazy things happening like breaks in it or gaps or jumps or all of a sudden this weird turns. As long as it's smooth, kind of like with curves, polynomials, things that we studied, sine curves, nothing crazy. The thing is, in mathematics, mathematicians can create very complicated functions that do things that don't behave like anything you would ever think of. And because of that, we have to categorize the types of functions this works with. For like I said, for real world applications, you usually don't need to worry about all this stuff. But to be precise, we have to state it in a theorem. That make sense? Like these weird, obscure cases. Because some mathematician will be, oh, well, this theorem doesn't work with this function. And they'll create some crazy-ass function that breaks the theorem down. So we have to add all these conditions to make it work. All right? So piecewise smooth surface that is bounded by a simple closed piecewise smooth boundary. Same thing, just to make sure everything stays together. All right, let F with positive orientation. So what we're going to do is this. When we have a surface in three-dimensional space, which again, this is going to be hard to draw, all right? What we want to imagine is that if the normal vectors, say the normal vector is pointed this way, all right? Let's say that's the way the normal vector is pointed. Then what we want the positive orientation of the curve C is going to be like if we were walking on the surface, we would want to be walking on the surface and look to our left and we would see the surface. And that would be positive orientation. So this guy can walk either this way around or this way around, right? So which way is he going to need to walk if we're going to all follow the convention that the surface needs to be on your left side? It would look like counterclockwise here, right? Yes? Now, if he was on the other side of the paper, standing upside down, right? Then if he's looking down onto the surface, is the surface on his right-hand side? I mean, on his left-hand side. If he's walking this direction. So look, these two guys are walking, right, like this. They're walking along this curve. This guy on top, the surface is to his left, right? The guy on the bottom, the surface is to the right, but he's walking in the correct direction, isn't he? If he were to walk with the surface to his left, then he would have to walk this way, right? So which way is it? Is it this way or this way? Well, the normal is what's going to dictate that. You want to be basically standing in the same direction as the normal. So this guy's on the wrong side of the normal. You with me? Okay. So, all right, we've got this curve C, everything's oriented, and we want to know the work done by moving around the curve. So we want to basically walk around that curve and calculate the total work through that vector field. Well, and if you don't want to do that and you want to switch it to something better, you can just do the double integral, the surface integral. Okay, so this right here, do you agree that the curl of f is a vector? Yes? The curl of f is a vector? The div of f is a scalar. but the curl of f is a vector. So this is the formula we were using for the last section, right? This was our formula from last section. The surface integral over S of f dot ds. That was flux, yes? This theorem says if we want to do work over a curve in three-dimensional space, you're going to wind up doing a surface integral with respect to surface area, right? This is from last class. But this now is your f. Your f is actually the curl of the vector field. And if you don't remember the computation of curl, here's what curl was. Curl was del crossed with f. You do the del cross f. This look familiar? And this is what happens when you actually del cross f. And there's a particular part of that del cross f that should look familiar. Green's theorem was this last component. That was the last component. And if you look at it this way, you can tell where Green's theorem comes from, because if you take the vector field in two-dimensional space, PQ, there was no R, right? That means if we extend it to three-dimensional space, you would have this, wouldn't you? And if you ask now for the curl of F, then you would take del, which is partial with respect to x, partial with respect to y, partial with respect to z, and you'd cross it with PQ0. And then when you did this computation, let's see what we would get. We would get partial of y partial with respect to y of 0, which would be 0. And then partial with respect to z of q. But look, remember, f in two-dimensional space will not have z's in it, will it? Right? I'm trying to show you where Green's theorem comes from. So the partial with respect to z of q should be 0 also, because that q won't have z's. So that would be 0. We get our first part would be 0. The second part, cover this up, we're going to get partial, however you do this, partial with respect to z of p again would be 0, and this one would be 0. So we're going to get 0 here. And then what would our last piece be? Partial of q with respect to x minus partial of p with respect to y, right? Which is this piece right here. That's all you get. And according to the formula, I can, instead of doing curl of f dot ds, I could do curl of f dot n ds, right? Because that's just this formula, isn't it? With curl f in here instead. And if I do this formula instead, what did we say the curl was? 0, 0, and then partial q with respect to x minus partial p with respect to y. Yeah? I know I'm working through this quick. I wasn't even going to mention this, but I want to now. What's the normal vector? If you're in two-dimensional space, but we've extended it to 3, your surface is on the xy plane, right? Which means your normal vector is what? Coming out at you. It's on the ground, let's say like that, right? The xy plane, laying down, your normal vector would be like this, which would be the vector 0, 0, 1. And when you dot those, what do you get? Partial q with respect to x minus partial p with respect to y, right? And then ds, right? So you'll have s ds, but because the surface is on a flat sheet of paper, s is a. So it's a dA, or the region dA. So it's just Stokes theorem in two-dimensional space becomes Green's theorem. All right, let's play with this one and do a couple of examples here. See how many I can do. I don't remember which came first. The proof of Green's theorem. There's a proof for Green's theorem that's pretty cool to see. Stokes' theorems. So, I'm trying to remember what the proof looks like. I don't know which one came first. All right, let's do an example. All right. Find the line integral, right, over C, the vector field, f dot dr, where C is the triangle with vertices 1, 0, 0, 0, 1, 0, 0, 0, 1, and the vector field is given. So let's start by drawing our triangle in three-dimensional space. Our triangle in three-dimensional space. X, Y, Z should be out one on each of the axes and then connected together. This is our triangle. And I need to add something here for you. I want us to basically go along this curve from that point to that point to that point. So I'm telling you that. Okay, I forgot to state it in the problem. Okay, so we're going to be moving along from here to here to here to here like that. So my surface, so I could do this line integral, right? I could, what I'd have to do is break this up into three separate line integrals. I'd have to go, like C1 would go from here to here, C2, and then C3, and I'd have to compute those line integrals. And maybe I could do it and it wouldn't be that bad. But is this a candidate for Stokes' theorem? Well, is there a surface there that, can you think of a surface, any surface, that has that as its boundary? That triangle, right, which is really a plane, isn't it? That's a plane. So this up here, this right here, I could call this S. Now, we need to somehow describe S a little bit here. Because I need... Find the what? Okay, so like, take your vectors, cross them, get your thing, find the plane equation? Yes? We could find the plane equation. I agree. We could cross some things, but maybe we can get that plane equation just by thinking about what it should be. Like, what should the value of x be when y and z are 0? If y and z are 0, what does x need to be? Okay, when x and z are 0, what does y need to be? Okay, and when x and y are 0, what does z need to be? 1? So how about just this? X plus y plus z equals 1. Without having to do cross products and all that to get normals, and I think we can intuitively just say, yeah, that's the equation of that plane. Yeah? Just saved us about 5 minutes, all right? Okay. Now, let's remember what the theorem says. It says the line integral over C of f dot dr should be equal to the surface integral over S of curl of f dot ds. Okay, that is Stokes' theorem. One of the first things you want to do with this is try and calculate the curl of f, because maybe, I mean, what if it's 0? Like, bam, we're done, right? That'd be wonderful. Let's try it. What is the curl of f? I'm going to erase this. This is just to remind us of what was. I'm going to move this up. S was x plus y plus z equals 1. And then del cross f is going to be partial with respect to x, partial with respect to y, partial with respect to z. And then my vector field is x plus y squared, y plus z squared, and then z plus x squared. And then I do my cross product. It's going to be a vector. So I cover up this one. What is the partial with respect to y of this? 0. Partial with respect to z of this? Negative 2z. Remember, you subtract that second piece. Negative 2z. You cover up this one. And then you go here, 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 and then negative, or you can go here, here, minus here, here, and keep the signs. However you want to do it. We've done this enough, though. What is it? Negative 2x. And then the last one, you should get negative 2y. Okay, that's the curl. Now what? I want you to understand that this is now, I understand this is the curl of f, but this is really like the vector field was in the previous section now. Because the previous section was surface integrals, right? Flux, and the field was f. In this problem, we're doing work, but to do work, we turn it into a surface integral where we're going to be using the curl of f as our vector field. Understand what I'm saying? Okay, so really here's where we are. I'm going to kind of erase this. I need more room. I think what I can do is make this smaller. So right now we need to do the double integral over s of this curl of f, which is negative 2x, negative 2z, and then negative 2x, and then negative 2y ds. That's what I'm trying to do. Now, how I do this ds is up to me. I can do normal vector over to ds like this, or I can do this, or I can do a special case, depending on what I have here. So what do you want to do? Okay, we could do normal vector if you know the normal vector. Do we know the normal vector for that surface? 1, 1, 1? Yes? One thing you have to be extremely careful with there. That is a normal vector, but it's not a unit normal vector, right? So remember I, j, and k when we were using those earlier? It was like, I was coming out of us, or negative I, or we used k, I think, or negative k. Those were all like 0, 0, 1 or 1, 0, 0. Those were all unit vectors. Yeah, so we have to actually take the normal vector coming out of this plane, which is the vector 1, 1, 1, and we have to find its length. The length of that is the square root of the sum of the components squared. So it's, root 3 divided by its length, right? That we can use as our normal vector. So y'all want to use that? You understand where that comes from? Okay. Does it make it any better? Let's see. It's still the integral over s. We're going to have negative 2x, I keep on saying x and writing x, it's z. Negative 2y, and I'm going to dot that with the unit normal vector. The unit normal vector. Y'all know where the 1, 1, 1 came from? The equation, right? X plus y plus z equals 1. The numbers in front of x, y, and z give you the normal vector. Okay. So it's this vector, but I have to scale it by 1 over root 3, right? 1 over root 3? I'm going to put that out here, 1 over root 3. That's just going to come out of the whole thing, and I'm going to dot it 1, 1, 1. Like that. D what? Capital S, vector or no vector? No vector. Okay? And now when we dot product that's pretty nice. We're just going to get negative 2z minus 2x minus 2y, right? But it's all scalar now. And what about that negative 2? It's in every one of them, right? You just take it out. So we get negative 2 over root 3 times double integral over s still of x plus y plus z, right? I pulled out a negative 2. D s. Any ideas? Turn into 1? Turn that into 1. Why? Because that's the equation of the plane we're on, right? This is 1. Go back to the plane equation. X plus y plus z equals 1. That means this is 1. So you get negative 2 root over root 3, and then S1 ds. And what is that saying? Once the surface area of the triangle, okay, so the triangle, the tilted triangle or the triangle on the ground? The tilted triangle. The triangle on the ground is if we had turned this over into D, which would have required we had done the shortcut. But we didn't do the shortcut. We went with the dot n, and this is where we are right now. Okay? Well, do you know the surface area of S? Do you know it's surface area of a triangle in three-dimensional space. So how could we get the surface area of this if we wanted to? So you could create a vector right here. You could create maybe a vector right here and a vector right here. And then you could call those maybe, let's see, we're not using U and V. We could define those as U and V. And then we could find their cross product and then take their magnitude and take half of that. Because remember, the magnitude of a cross product of two vectors is the area of the parallelogram spanned by the two vectors. So you could just take half of that area. Now, could we get those vectors pretty easily? I think we could, because we know the points, right? Like this is the point 1, 0, 0. This one's the point 0, 1, 0. This one's the point 0, 0, 1. And so what's U? -1, 0, 1. And what's V? The vector from there to there. -1, -1, 1, 0. And what would happen if you crossed these? Cross those, you get 0, you get -1, and you get, cover that up, you get 0, -1, 1. Yeah, but you have to switch it. So -1 again. And then, what's the last one? -1 again. Then take its magnitude. What's the magnitude of that cross product? Equals root 3. And then we want half of that, right? Because that's the area of the whole thing? Okay. So divide by 2. So this right here becomes -2 over root 3 times the area of S, which was root 3 over 2. So you get -1. That's one approach. And that's because somebody wanted to use the normal vector in the beginning. And we got it, right? Just for practice, though, let's try doing the same thing without using the normal vector. So let's go back. I want to go back to this point right here. And this time, let's use one of the shortcuts, not the normal vector. There's nothing wrong with using the normal vector, but here's what I'll warn you of. If you're going to use the normal vector, you better be able to find the area of S. Because if you can't find the area of S, it's going to be problematic. Unless everything works out perfect. Does that make sense? In this case, we got lucky because we can find the area of S. Okay, going back to this. So I'm looking at this formula right here. I'm going to use the special case that I know that my surface S, is this equation, right? And that means it could be written as x is a function of y and z, or you could solve for y and say y is a function of x and z, or you can solve for z and say z is a function of x and y. So I'm going to do it the way that we like. I'm going to say that z is a function of x and y, and it will be 1 minus x minus y, right? That's the equation of z for z. Pardon? Yeah, I don't know why I put yz. X, y. All right, and then the formula we would use would be, why did I erase them? I don't know. Would it be this one? Yes. This one right here? Are our normals pointed properly? Up. Well, the normals on this little plane are pointed up, aren't they? Up a little bit. They're not pointed down. So I could use that formula. So this would become the double integral over what? D. Now D is going to be the variables controlling the surface, which are x and y, right? And then I'm going to have negative p. What's negative p? Be very careful here. What's negative p?
Negative x minus y.
So is this p or is this p? This is what I was trying to say earlier. You cannot confuse what's going on here. This is originally this vector field. This would be PQR, right? But because I'm using Stokes' theorem, I'm turning that integral, that line integral, into a surface integral where the vector field I'm using for the surface integral is the curl of f. So this is P, Q, and R for us. All right? Forget the line integral now. We are now doing a surface integral, and that vector is our PQR. So what would negative p be? 2z. 2z, and then we have partial of g with respect to x. Partial of this with respect to x, negative 1. Then we have minus q, which would be negative 2x, so it'll be plus. And then partial g with respect to y, which is another negative 1. And then plus r, and r is negative 2y. D A, okay? Our domain variables are now x and y. Our domain is on the ground. It's no longer the surface. It's the ground, the shadow. So what does this clean up to be here? Double integral over d. We've got negative 2z. We've got negative 2x. And we've got negative 2y. dA. I can pull out a negative 2. Double integral over d of x plus y plus z dA, which is just 1. Again, isn't that? That's 1. So this is negative 2 double integral over d of 1 dA, which is the area of the region D, which is the ground. It's the x and y triangle on the ground here instead of the one sitting up in space. See, notice that what we have not had to deal with, by going with this shortcut, we have not had to do that scaling of 1 over root 3 with that normal vector. And in the area of this triangle that was tilted, we got a root 3 in there, right? So they canceled each other out. But by turning this into this shortcut, we're not dealing at all with that aspect of it. And it's just turning into the area of the thing on the ground. And what is the area of the thing on the ground? It means what? 1 unit out, 1 unit up. So base times height is 1. Half of that is just a half, right? So this becomes negative 2 times a half, which is negative 1. That's the same answer we got the other way. That seemed a little bumpy, huh? I mean, just maybe we would have been done with the line integrals by now, like if we had not used Stokes' theorem, but highly unlikely that you would have enjoyed that. Questions? We should be able to get through this one. All right, find, again, the line integral, f dot dr over this curve C, where C is the circle x squared plus y squared equals 16. Isn't x squared plus y squared equals 16 in three-dimensional space? That's a cylinder, right? But we're fixing z to be 5, which means it's just a circle moved up 5. Yeah? So we originally had a cylinder, right, like that. But if we fix our z to be 5 on that, we're just going to get this piece right here, which we'll call C. It's not really tilted that much. I don't know why I tilted that like that. Z is 5. That means it's like flat, right? So it's parallel to the xy plane. It's parallel to the xy plane. Okay, so that's our curve C. So could we not use Stokes' theorem here? We could find a parametric representation of this curve. We could call that R of t, not R of uv. These aren't surfaces, these are curves. We could find R of t. Then what we could do is we could evaluate our function at R of t. We could dot that with R prime of t and integrate that with respect to t. You have to go back and look up and remember what this formula really means. So do you really feel like calling that thing, what would this R of t be? 4 cosine t, 4 sine t, and then 5. That would be those would be your component functions that would draw this curve. Then you'd have to go and take this vector field and replace every x with 4 cosine t, every y with 4 sine t, and every z with 5. Take that, plug them in here. You'd have to take the derivative of 4 cosine t, 4 sine t, and 5, right? Take that derivative and dot product it with this thing, and then integrate that. And that would not be fun to do at all. Let's see how Stokes' theorem works with this. We do see a surface here. Do you? You see a surface? Yeah, it's right here. And also, on this instructions, I didn't tell you the path. I wanted it to be this way. Okay, so that's not given in the problem the way I stated it, but the path is like this. So our positive orientation, our normal's coming up like that. In the book, when you do your homework, it says, let the orientation of C be like counterclockwise when viewed from above, which is what this would be, right? If viewed from above, the orientation of C is counterclockwise. All right, so let's talk about that surface S. What can you tell me about that surface S? It's a nice surface, isn't it? It just says Z is 5, right? I mean, that's it. That's the equation of that surface. Z is 5. I like that surface. Not only that, we could use the shortcut. We could also use the normal vector because that's a nice normal vector for it, right? So I'm going to have some options when I get to that point. But what is it that I'm going to be using for the surface integral? I'm not going to be using f. I'm going to be using the curl of f. So let's compute the curl of f. All right? Curl of f. Del cross f. And for convenience, I'm just going to do it right here. So here's partial with respect to x, partial with respect to y, partial with respect to z. And I'm going to do that right here. So cover this up. What is the partial with respect to y of this? X e to the xy. Okay, and then minus this and this together, right? So not multiply, but the partial. So 2x. Okay, now, next piece. Do y'all see that none of this is really going to matter if I use this vector? Do y'all see that? The first two components aren't going to matter. But let's do the work. Okay, so this right here, when I do that, y minus y e to the xy. That'll be your second one. And then your last one, cover this up. So 2z, that's the important one, 2z minus z. So this is the vector field that we are going to use in our surface integral. So we are going to do the surface integral over S, which I didn't label. Here's S. Of this vector field, x e to the xy minus 2x y minus y e to the xy, comma, just z. And then now my choice, ds here, I have some choices. I can do n normal dot, right, dot normal ds, or I can do shortcut, whatever. I'm going to do the normal dot, right, because it's just going to work out. So I'm just going to go straight to it. Dot. And I'm not concerned about having to scale this because this is a unit vector already. ds. Okay. Now, when we dot that, it just becomes surface integral over S of z ds, d capital S, which is just what? 5. It's just 5 because z is 5. I erased it, but z is 5. Which is really just 5 double integral over S of 1 ds, which is the area of the surface S, right? The surface S, which is this up here. But because it's flat, it's the same as the area of a circle on the ground. So it's just pi r squared, right? So this is 5 times pi times, what's the radius of that circle? 4 squared. So 16 times 5 is 80 pi. That's your flux. Or that, sorry, no, that is not your flux. That is your line integral. That would be the work done moving a particle along that curve through a vector field. All right, well, let me see how many more examples I have. I only have one more example. And then that's the homework for that section. And then we get the divergence theorem. I told you at the end of class I would start talking about the final, so we've got 3 minutes. Let me just mention some things. So I brought up a couple of finals. I was looking at these earlier today. So if you want, you can write this down. You don't have to, but I'm going to mention some things that were on it. 2 separate finals, 2 separate years that I gave finals for this class. One of my finals was 6 questions long. I don't know why, but I mean, so the first question I asked had to do with finding the equation of a tangent plane. Now, I'm not telling you this because this is exactly what you're going to expect, but I want to give you kind of a feel for what I've asked in the past. So I gave them a vector surface, r of uv, and asked them to find the equation of the tangent plane. Then I gave them a vector function r of uv. It was somewhat complicated. And I asked them to find the surface area. So they had to know those formulas, right? Then I gave them a surface that was one of the special cases. In this one, it was that... Oh, well, yeah, it could have been looked at 2 different ways. But I asked them to do a surface integral over a scalar function. Surface integral over a scalar function. That was before flux. All right, we talked about that. Then the next question, I asked them to find the flux. I give them a vector field. I give them a surface. Very much like that paraboloid problem we had when we started class where it was faced sideways with a little disk. And I did not tell them how to do that problem. Like I didn't tell them you can use divergence theorem. I just gave it to them. Then number 5, I gave them a line integral and I actually told them use Stokes' theorem. And on the last one, I gave them another problem to do the flux, and I told them to use the divergence theorem. I must have been nice back then.
Can you go back to that?
Mm-hmm. That was 2012 when I gave that final. And then one of the more recent ones was 10 questions. Most likely this was a final I gave during a summer. My summer populations are a lot different than my normal semester populations. It's just very different. So, okay, so first one I asked them, Lagrange. Find the maximum values of a function with a given constraint. That's 11.8 was that section. And I gave them another problem where were given a double integral, and it was like a type 1 region, and they had to actually convert it from type 1 to type 2 and rewrite the integral. So it was like we did this I think one time where we had a region, it was like, oh, that's type 1, and if you try and integrate it, it doesn't work. But if you change it to a type 2, the order of integration switches, and it becomes an easier integral to do. Number 3, find the volume, a triple integral with respect to volume of a scalar function. So this is just triple integrals, chapter 11. And then line integrals. Not on a closed curve, so they had to do the whole thing. Find parametric representations for the curve. Then I actually told them on the next one, find this line integral using the fundamental theorem of line integrals. But I did not give them what? What would they need in order to do that? Well, I gave them the endpoints, but I didn't give them the potential function. So they had to find little f. They had to actually do the partial integration. And then number 6, I gave him this another line integral, and I gave it to him over this closed curve. And so they probably should have used greens for that. Then I asked them to find the surface area of a cone. So this is in the section for parametric surfaces, R of uv. There was a formula we had for surface area. Anyone remember what it is? How you find the surface area of a surface S? Double integral of 1 ds, right? That's what we did. And does anyone remember what that d capital S really is? It's with respect to surface area, but when you actually do this problem, it's the square root of 1 plus the partials. You have to go back and look. Yeah. Okay, and then the 8th one, find the flux across a surface. It was not across a closed region. And then number 9 was a Stokes's, and number 10 was a divergence. That's a long test. But you have 2 hours, 45 minutes. I would expect that your test is going to be somewhere between those two. Like, 8 problems to 8 to 10. I don't think 6 is enough, but I think 8 to 10 is good. But just keep in mind, it could go back, we could go back to 11.8 is the furthest I'll go back. Have a good day. Yes?
Maybe that can make something where you can get over, or you can go over 10.
Where you can go over what?
Basically, like you get more questions and we pick our 10 or 8. And then you get extra.
I don't know. I mean, I'm really hoping to make a final where I don't overload you with questions and what you do is good quality work, rather than giving you pick from these and 130 points possible. I would just expect to have to do it all. Yeah.
And then for the bonus questions and the homework that we bring to the day of the examination, will you do that?
Just bring them. Yep. We'll see you on Wednesday.
The finale of the class.
The finale of the book.
How great that
You get to finish that off. Do your homework. I know it's hard towards the end here, but do your homework.
That's all I'm doing all weekend.
That's all I'm doing all week.
What do you mean? Like, oh, to try and find your stuff? Just wait around. The ladies that's going to come in, her name is Heidi. She teaches. Yeah. If you wait around, she'll come in, she'll unlock the door, and just come in and ask her. You looked around, lost and found nothing?
I looked at all the offices in this, and in the live oak, and no
What was in it? I mean, just, it was your work? But did you have valuables?
He told me it was going to be the
not
17th.
as far as like personal information,
And it's not. It's
but it's just really all my study materials.
Who would want to?
I think because I find it hard to avoid seeing a journal line.
Yeah. Okay, well, you can wait if you want to talk to her. Just wait outside for her. Yes, ma'am.
So you put my grade in wrong and you put like 90 out of 10, so I have like a way higher grade than I'm supposed to.
90 out of, oh, instead of 9 out of 10?
Yeah. So
Okay.
I hate to tell you because
You didn't want that? Well, you know what? It would have, the system, when I do a final thing, it will tell me this grade is out of norm.
Okay.
So, thank you. I'll take a look at it. Yeah.